All right, I'm just going to go through and just start doing examples. We're going to be using the trace determinant plane in these examples to determine the stability of these systems. So my first example is the derivative of x is 1413x. It's 2 by 2, so I can just look at the trace and the determinant. Trace is 1 plus 3 is 4. Trace is positive, so I know it's going to be unstable. So this was a stable oscillations, stable sink, and here was a saddle. Here we have, because t is positive, I know I'm either in this or this region. This is saddle, unstable source, or oscillations in source. I don't know where I'm going to be there, so I got to find the determinant. But I can tell you already it's going to be unstable. Determinant is going to be 1 times 3 minus 4 times 1. 3 minus 4 is minus 1. So that means I'm down here, the determinant is negative, and without doing anything else, I know it's going to be a saddle. And it's going to be unstable. Another example. Suppose the derivative of x is equal to matrix times x, and the matrix is 3, 7, minus 6, minus 5. Trace is going to be 3 plus negative 5 is negative 2. Oops. Trace determinant. So trace is negative, so I know it's going to be, if the determinant is positive, it's going to be stable. It could be oscillating and stable, or it could be a sink, but it could also be a saddle, which is unstable. So I don't know yet. So I need the determinant. So 3 times minus 5 minus 7 times minus 6. This could be minus 15 plus 42. This can be what? 32, 27, is that correct? 27, according to my notes. So the determinant is positive, so it's stable. It's either going to be in this region or this region. I just need to, let me just be careful. So it's stable. It's either a sink or it's going to oscillate. I don't know yet. I have to now compare t squared over 4 to 27. So t squared over 4 is going to be minus 2 squared over 4. 4 divided by 4 is 1. So in this case, 27 is greater than t squared over 4. So this parabola is t squared over 4. So my t is minus 2. So I'm somewhere along that line. This point right here is going to be the point t is minus 2, d is 1. And since d is 27, that means I'm up in there. It means it's going to be stable with oscillations. Again, the only thing I did was take the trace and the determinant, none of the eigenvalue calculation stuff. Easy peasy. If only it was easy, right? Not easy, but it's not as involved as what we did before. So this is very similar to stuff we said before. The question is given k, if you give me any value for k, what's going to happen to the stability of this? Fine. Okay. So let's find the trace. 1 plus 0 is 1. So it's unstable. I know already it's going to be unstable. So if I plot my trace determinant plane with d equals t squared over 4, I know the trace is 1. So as I change my k, I could be, well, I don't know yet, but I'm going to be somewhere on this line, which means that as far as we know so far, it could be oscillations in growth, could be growth in both directions, which would mean a source, or I could have a saddle. I don't know. But basically, I'm going to find the determinant, and I'm going to ask for what values of k is going to put me in this region, or this region. So what is d? D is going to be 1 times 0 minus 1 times k. It's going to be minus k. Now notice k could be any number, positive or negative. If k is positive and growing, I'm going to be moving down this direction. It's going to get more and more negative. And as k is negative and getting more negative, negative of that's going to be positive, so I'm going to be moving off in this direction. So I can go through any region on here. So now my question is what are the cutoffs? So if d is less than 0, it's going to be a, we call this a saddle. In this case, t squared over 4, t is 1, so it's 1/4. So if d is between 0 and 1/4, it's going to be a source and unstable. And if d is greater than 1/4, it's going to oscillate and be unstable. So now I got to translate that into k's. All right. And then, yeah, that basically takes care of d positive. I did not take care of that yet. I'm going to come back and do that. All right. So let's do this. Let's do this region first. So for oscillations and unstable, d has to be greater than 1/4. What is k? Or d is k. Sorry, d is minus k. So that means minus k is greater than 1/4. And if I multiply both sides by -1, k is less than -1/4. So if k is less than -1/4, it's going to oscillate and be unstable. It's going to be unstable source. That means d is between 0 and 1/4. D again is minus k, so 0 is less than minus k, less than 1/4. Multiply through by -1, I get 0 is greater than k, is greater than -1/4. And that's going to give me my unstable source. And then finally, for my saddle, d is less than 0, d is minus k. Careful, sorry. D is minus k, so minus k is less than 0. Multiply both sides by -1, and I get k is greater than 0, and that gives me my stable, or my saddle, which is unstable. All right, so let's pull all that together. We were originally asked, what's the stability characteristics of a system where the matrix is 1k, 1, 0. It's 2 by 2, so we can use the trace determinant plane. We just found that for different values of k, if k is less than -1/4, it's going to oscillate and be unstable. If k is between 0, oops, I can be careful, k is between -1/4 and 0, then it's going to be an unstable source. And if k is, greater than 0, it's going to be an unstable saddle. All right, so for different values of k, if k is less than 1/4, it's unstable with oscillations. Between 1/4 and 0, it's an unstable source. And k greater than 0, it's an unstable saddle. And the way we got that was looking in the trace determinant plane. So this was d equals 1/4 t squared we had t was equal to 1. And as k changes, you're going to be moving onto different points along this vertical line. And what this was at, this cutoff was at 1/4, and this cutoff was at 0. So these different regions correspond to this region, and that region. Okay, one last example. This is going to be very similar. We're going to see what happens, see what a small change can do. So this is a k, minus 1, 1, 0. So the question is what happens to this for different values of k. K is any real number from minus infinity to infinity. You give me a value of k. I want to know what is going to happen in terms of its stability. So at the end, what I'm looking for is a table that just lists out all the possibilities, and I just have to look up where does k stand in this. So what's the trace? Trace is k plus 0 is k. So I immediately see that k could be positive or negative. So there's a lot of different things that could be here, depending on whether or not the determinant is positive or negative. So this is not that helpful. The determinant is going to be k times 0 plus 1 times minus 1. So that's 0 minus a minus. That should be a minus 1. Minus that. Minus a minus 1 is 1. Whew. That was harder. So the trace, as I change k, is going to take on all possible values. So if I look at my trace determinant plane, the determinant is 1. And as I increase k, I'm going to be moving off in this direction. As I decrease it, I'm going to be moving off in this direction. So my possibilities are going to be 4 different things. Out here, I'm going to have a stable sink. Here it's going to be stable oscillations. Here it's going to be unstable oscillations. And this is going to be unstable sink where both eigenvalues are positive. So the question is, if you give me a value of k, do I fall in here, 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 or here? So let's see. Let me figure out what's going on. So here, so this is t equals 0. This is going to be, so what is this? This is d equals t squared over 4. And this is 1. So let's see. We have, if d is 1, what's t if it equals t squared over 4? If I multiply both sides by 4, I get 4 equals t squared. So t is plus or minus 2. So this is minus 2 and positive 2. So if the trace is less than negative 2, I can get a stable sink. If the trace is between minus 2 and 0, I'm going to get stable oscillations. And if the trace is between 0 and 2, I'm going to get unstable oscillations. And if t is bigger than 2, it's going to be an unstable source, and this was wrong. That should be source. Sorry about that. So in this region, it's unstable and it's a source. Okay. So at this point, we have the derivative of x is equal to a matrix k minus 1, 1, 0 times x. Trace is k. The determinant was 1. We know if t is less than minus 2, it's a stable sink. But the trace is k. So if k is less than minus 2, there it is. If my trace is between minus 2 and 0, then it's stable and it's oscillating. So if k is between minus 2 and 0, that's going to be what's happening. And if t is between 0 and 2, it's unstable oscillations. So k is between, again, since the trace is 2, that's just plugging in k. So if k is between 0 and 2, I get unstable oscillations. And if t is greater than 2, it's an unstable source. So that means k greater than 2. So in terms of what happens for k, if t is less than minus 2, I get a stable sink. If I'm between minus 2 and 0, I get stable oscillations. If I'm between 0 and 2, I have unstable oscillations. And if I'm bigger than 2, it's an unstable source. So given k, if k is less than minus 2, it's a stable sink. K between minus 2 and 0, it's stable with oscillations. K is between 0 and 2, it's unstable with oscillations. And k greater than 2, it's unstable, and it's a source.